It's revision show time. Welcome to tonight's revision show on the Joy Learning television channel. You can catch us live on Facebook and YouTube, Joy Learning Television. My name is Anepabi Albert. You can call me Pius. And tonight I'm going to take you through revision in physics as we prepare for the forthcoming WASSCE examination. Do you know that teachers who have observed, they've taken analysis of the kind of questions that WAEC asks students in exams, and with their experience, they advise that students should answer some particular kind of questions. They should prepare and answer those kind of questions. Are you aware of that? Then, one of those questions, or one of those areas, is atomic and nuclear physics. If you should prepare very well to go and answer questions on atomic and nuclear physics, the chances that you're going to score more than 80% of the marks for question number 12, atomic and nuclear physics, is very high. So tonight, I'm going to take you through some portions, some aspects of atomic and nuclear physics. And if you should take it so seriously, I am very sure it's going to help you to come out with a very good grade as far as the WASSCE physics exams is concerned. So stay glued with me. Let us do a recap of the things you have learned right from SHS 1, and then let's prepare for the forthcoming exams. You can call other friends to also tune in and enjoy the lesson. Now, as the lesson gets to its tail end, I'm going to give you the chance to call in and answer what we call the problem of the day. So before we start tonight's lesson, let us take time and go through the problem of the day. The first one says, list 3 evidences to support the claim that X-rays are electromagnetic waves. So, as the lesson goes on, we will look at what we call X-rays. And then you should be able to tell me why X-rays are, or they form part of electromagnetic waves. Next one says, light of wavelength 4.5 times 10 to the power minus 7 meters is incident on a metal, resulting in the emission of photoelectrons. If the work function of the metal is 3.0 times 10 to the power minus 19 joules, calculate I, the frequency of the incident light. Then II, the energy of the incident light. Then III, the energy of the photoelectrons. That is our problem of the day. You'll be given additional information that speed of light, here it should be speed of light in air. 3.0 times 10 to the power 8 meters per second. Then H, which is Planck's constant, is 6.6 times 10 to the power minus 34 joule second. That is the problem for tonight's revision show. Try to take a shot of it and try your hands on it as we go through the lesson. I'm very sure that when I open the phone lines, you will call to give me answers to these questions. All right. This is also a past question, so it's a likely examination question. WASSCE June 2018, questions 12B and D. Good. So let's get the ball rolling. Tonight, I'm going to look at the law of radioactive decay, an aspect that most of the times may confuse or may trouble students. So I'm going to take my time and take you through it step by step. Make sure that you follow all that I'm going to do tonight. And I'm very sure that after the revision show, when you lay your hands on any questions on radioactive decay, you will be able to answer. All right, what does the law say? The law of radioactive decay says that the rate of decay, of a radioactive nuclei is directly proportional to the amount of radioactive nuclei present at that time. The rate of decay of a radioactive nuclei, how fast or how slow a radioactive nuclei will break down or split open or will decay depends directly, okay, on the amount of the radioactive nuclei that is present at that time. So if you have a radioactive nuclei in a huge or large amount present at a particular time, it will decay at a faster rate as compared to one that is in smaller quantity at a particular time. That is the law of radioactive decay. So you have to keep this law because that will help you to write mathematical expressions of the law. So mathematically, we want to put this law into an expression. It says that the rate of decay of a radioactive nuclei, okay, so the rate is how much of the nuclei decays per time, per change in time, is directly proportional to the amount of radioactive nuclei present at that time. So we want to use n to represent the number of nuclei initially present in a radioactive sample, right? So the law can be written as dn on dt. This is the rate of decay. dn, change in the amount of radioactive nuclei present. dt, with change in time, is directly proportional to the amount present at that time. So the whole law can be summed in this. The n on dt is directly proportional to n, right? So the n on dt is our rate of decay of the radioactive nuclei and is directly proportional to n, the amount that is present at that time. So the n equals the amount of nuclei that decays, and then dt is the time interval. Let's move on. So the n on dt together gives us the rate of decay. So the expression that I just wrote, which is the n on dt is directly proportional to n, this expression can be written as the n on dt is equal to minus lambda n. So here I have changed the sign of proportionality, this sign, and I've brought in an equal to sign, and I've introduced a constant. Here the constant is lambda, called the decay constant. So lambda is equal to decay constant. I can't work with a sign of proportionality, so I change into an equal to sign. And to take care of whatever errors might come in the equation, I introduce a constant of proportionality, which is the decay constant, lambda n. So why do you have negative sign there? The negative sign indicates that as decay goes on, during decay of a radioactive nuclei, the nuclei present, the amount present, decreases with time. So if you have a radioactive nuclei and it is decaying, as time progresses, as time increases, the amount that is present, the amount that is left, will be reducing with time. So the negative sign only indicates that the amount of radioactive nuclei present as decay goes on decreases with time. So our decay equation, or our decay equation, gives us the n on dt is equal to minus lambda n. You don't have to forget this expression. It's very important. All right, let's move on to higher things. Now, decay constant. We just wrote an expression. The n on dt is equal to minus lambda n. And we are saying that lambda is the decay constant. So if lambda is a decay constant, that's it. What will be our definition of it? Well, we can try and make lambda the subject from the expression. So from the n on dt equals minus lambda n, let us make lambda the subject. So I can say lambda will give me minus into bracket the n on the t, right, all over n. How? I try to divide what I have on the left hand side by n, so that lambda will stand alone, but there's a negative sign there, so the negative also goes to the other end. So if I have lambda, which is my decay constant, being equal to minus into bracket the n on the t all over n, I'll just forget about the negative in my definition, because it is only telling me that the amount of nuclei that is left as the decay continues with time decreases with time, right? But the n on the t is the rate of decay, right? And n is the amount of radioactive nuclei what? Present. So what will be our definition for the decay constant? We will say that the decay constant is the rate of decay. Rate of decay refers to what? Refers to this, the n on the t. So it's the rate of decay of a radioactive nuclei per the amount of nuclei present at that time. So I could say it is the ratio of the rate of decay of a radioactive nuclei to the amount of nuclei present at that time. So lambda, which is a decay constant, is the n on the t, which is the rate of decay. So it's ratio of the rate of decay, that is the n on the t, on the amount of radioactive nuclei present, which is n. And that will be our definition for the decay constant. Now, the SI unit is per second. Why is it per second? Per second. Look at the expression given to you. You have the n on the t. Change in n over change in t, all over n. Change in n is just a change in the radioactive nuclei present. So up here, I'll get 1. If I look at units, change in n on change in time, time in second. And this is just 1 because I'm not going to get a unit for it. The number of atoms, radioactive nuclei present, so and so, a number of atoms. So no unit for them. So if I guess 1 on s, I'm going to get s to the power minus 1. And that gives me per second. So whenever you have the decay constant, you are asked to solve for the decay constant, you make sure that you attach the unit per second to it. Very important. All right. Now we can look at decay probability. When you are going to look at probability, then it means that you have what we call the sample space. All that is available for you to consider. Then you are going to pick something out of all that is available to you. So, decay probability, here in this case, I have n, which is the amount of radioactive nuclei present. Then part of it, okay, some of it will decay, which is the n, change in n. So change in n out of all the n should give me my decay probability. So we are saying that this is the ratio of the amount of radioactive nuclei that decays, which is the n. So all this, the amount of radioactive nuclei that decays is the dn, right? To the amount of radioactive nuclei present, which is n, at that time. So if you keep the n on n with you, the definition will come to you naturally. So it is a ratio of the amount of radioactive nuclei that decays to the amount of radioactive nuclei present at that time. Mathematically, I'm going to get decay probability is equal to dn over n, where the n is amount of radioactive nuclei that decays, and then n is the amount of radioactive nuclei present at that time. The decay equation. The decay equation. So we have to also take our time and look at that and keep the equation, because when you are asked questions, you will be required to use the equation to solve. And if you don't know the equation, it means you will not be able to solve the question. Right? So, what is the decay equation? These assumptions are very important. You have to know what represents what. Other than that, you won't be able to fish out the correct data, and that will affect your solution. So, in this case, we are saying that N naught is the initial amount of radioactive nuclei or atoms present. So, in the radioactive element, before the decay, there will be a radioactive nuclei present. So, the initial amount of that radioactive nuclei present, even before the decay starts, we are using N naught to represent that. Now, decay will take place. So, after a time t, the amount of radioactive nuclei or atoms left after the decay is N. So, N naught is what we have initially. Now, after it has decayed for some time, what is left is N. Now we are good to go. So, if you have N naught to be that and N to be this, then the decay equation is giving us N is equal to N naught exponent minus lambda t. Watch that carefully. Very important. N is equal to N naught exponent minus lambda t. So here N is the amount of nuclei that is left after some time of decay is equal to the initial amount of the nuclei that we had, exponent minus decay constant, which is the lambda, times t, which is time. So that gives us that. Okay, so that's our decay equation. We can try and get a graph. This graph is telling us something. Our N is the amount of radioactive nuclei, this one, that is left with time. But initially, we had N naught. So N naught is the amount that of nuclei you had before decay. Then the graph sags moves downwards, the curve moves downwards like this. It tells you that one, the decay of the radioactive nuclei is not really directly proportional to time. It doesn't mean that there is an equal amount of decay. You don't have an equal amount of decay of the radioactive nuclei with equal change in time interval. No. So it could be that at a point, there can be a point in time, you have much more of the nuclei decaying within a short time. Then at a point in time, there could be just a little amount decaying within a longer time. But we can also note that with time, as time progresses, if you look at the graph carefully, as time moves on, so from here, time axis, we are going forward this way. This N naught is rather coming down, it's reducing, it's coming down. So it is telling you that the initial amount of the radioactive nuclei present, which is the N naught, is decreasing, decreases, okay? It's decreasing like that as time progresses. And that's how the graph could be interpreted. Now we can move on to half-life. Half-life. The half-life of a radioactive element is defined as the time. So you see now half-life is time. It takes half a given number of radioactive nuclei initially present in a given sample to decay. The time that it will take half of a given number of radioactive nuclei initially present in a sample to decay is its half-life. So just imagine if you knew your half-life as a human being. If you know that maybe your half-life is, let's say, 60 years, oh, then you are blessed. It means that it will take you 60 years for half of your life to go away. So probably you're going to live for 120 years. That's quite huge. Anyway, so you have a radioactive sample. Let's say it has got 20 atoms. How long will it take it for 10 of the atoms to decay? That becomes its half-life. So the time it will take half of the initial amount of radioactive nuclei present in a given sample to decay is its what? Half-life. And we represent that one with T subscript half. Our other text could make it a capital T subscript half. So that's half-life. So mathematically, we're going to get half-life is equal to natural log of 2 on the decay constant, ln 2 on decay constant. Now, ln 2 is on your calculator. It's a first function. So you will see a button with IN, that's natural log, like that, on your calculator, like this. If you press, you can try it right now at home, and let's look at it. So if you press that, what are you going to get? Natural log of 2, so ln 2. What are you getting? So that we get to know the other expression for half-life. So I'm getting 0.69314, blah, blah, blah. So instead of writing half-life is equal to natural log of 2 on wavelength, is lambda. It could also be half-life T half is equal to 0.693 on lambda. If keeping figures is quite difficult for you, then stick to ln 2, stick to natural log of 2 on wavelength, because you have your calculator with you and you can always press punch natural log of 2 and get the value 0.693 on the decay constant. That's our expression for half-life. This one too is very important, and you don't have to lose it, because if you lose it, you may not be able to solve any question when it comes to decay constant, half-life, decay probability, and then the law of radioactive decay. Now, we can be asked to show why half-life is equal to natural log of 2 on the decay constant, which is lambda, or 0.693 on lambda. So let us try and look at the proof of that. So we are going to prove why, or how come you have T half is equal to natural log of 2 on the decay constant. So let's set the ball rolling. We come across the decay equation, which is N is equal to N naught E minus lambda T. So we got this as our decay equation, right? So after a period of half-life, what happens? We are saying that half-life is the time it will take half of the radioactive sample present initially to decay. So after a period of half-life, if still our N is the amount of radioactive nuclei present after the time of decay, and N naught is the amount present initially for decay, then what will be left after half-life, what will be left, which is N, will be equal to what we had initially, half of it. So like half of what I had initially is the same as N naught on 2. So you have to get this straight. Half-life here is telling us time that it will take for half of any amount of radioactive nuclei present to decay. Okay, and here we are using N0 to represent the total amount of radioactive nuclei that we have present initially before decay, and N is representing what you have left after the decay. So after half-life, half of what we had initially will be left. So what is left N is equal to half of what I had initially, which is equal to N0 on 2. Then the time will now become T half because it's half-life. So let's put this back into our decay equation. So I'm going to get N is now N0. So I'm going to get N0 on 2. N has now turned into N0 on 2. So in place of N, I have N0 on 2 is equal to, I have N0 there, exponent minus lambda. T is now T half. So T half. Right? Now, N0 is common to both sides. So this can go out with this. And that will give us 1 on 2. Right? Is equal to E minus lambda T half. I don't want to be keeping the negative sign here. So if I should make all this a denominator, I'll be able to do away with the negative sign. So I'll get 1 on 2 is giving me 1 all over E lambda T half. Is that okay with us? So on my left hand side, I have 1 over 2. On my right hand side, I have 1 over E to the power lambda T half. So in that case, I can just pick the reciprocals of them. And I'm going to get 2 is equal to E lambda T half. Now I can take log to both to base E on both sides. In other words, natural log of both sides. That's what we call log to base E. So if I have log 2 to base E, then here I'm going to get log E lambda T half to base E. Is that okay with us? Now, this is the same as natural log of 2 is equal to lambda T half, now log E to base E. So log E to base E will give us 1, right? So we're going to get natural log of 2 is equal to lambda T half. Now we are looking for half-life, T half. So we divide both sides by lambda. So T half becomes natural log of 2 on lambda. Good. Or since we know what we can get what natural log of 2 is, then T half will give me, with the calculator, you can get natural log of 2, 0.693 on lambda. So that is the reason for which, or that's the proof for which we are saying that T half, which is half-life, is equal to 0.693 on the decay constant, or natural log of 2 on lambda. I am pretty sure that when you are asked to show why T half equals 0.693 on lambda, or T half is equal to natural log of 2 on lambda, which is a decay constant, you should be able to do that without much difficulty. Good. So it's a good time for us to solve 1 or 2 questions based on all that we have gathered so far. I want to see whether we have got the understanding right. So example 1 says, a substance whose half-life is 1 year now has 1,000 atoms. This means that, so this is a question of understanding. The substance has 1,000 atoms. Its half-life is 1 year. It means that it will take 1 year for half of the atoms of this substance to decay. So after 1 year, you should have 500 atoms remaining. Yeah. Now, it means that if after 1 year, we're going to get 500 atoms left. After the next 1 year, which is now 2 years' time, know that every 1 year, half of whatever is left will go. So after 1 year again, half of 500 will go, which will be 250 atoms. Are you there with me? Good. Now, after another 1 year, okay, another half of whatever was left, 250, will go, which give me 125 atoms. Are you okay? Good. Now, we can also go forward and look at something else. If it now has 1,000 atoms, then probably 1 year ago, okay, it means that after 1 year now, half of it is the 1,000 that is we have now. So 1 year ago, how many atoms were there? Because after 1 year, half of it will go and now you have 1,000. So it means 1 year ago, we had 2,000 atoms of it. Its half-life is 1 year. So after 1 year, let's say now, half of it will go and then you have 1,000. All right. But the good thing is that we have been given some options to choose from. So in that case, let's look at the options. Option number 1. 1 year ago, it has 2,000 atoms. Is that true? Yes, it is true. It is true. Because the half-life is 1 year. So 1 year ago, it had 2,000 atoms. That is why now, after 1 year, it has got 1,000 atoms. So this is true. Fine, let's see. 2 years ago, it had 4,000 atoms. Okay, let's just try and see. 1 year ago, 2,000 atoms. Now, after 1 year, 1,000. So half is gone. 2 years ago, it had 4,000 atoms. So that after 1 year, it should have 2,000. Then after the next year, now it should have 1,000. So this 1 through is correct. It's a correct statement. 2 years ago, it had 4,000 atoms. In 6 months' time, it will have 500 atoms. Can that be true? It will, now, it has got 1,000 atoms, right? In 1 year, half of it should go to have 500. So in 6 months, it should not be 500. In 6 months, it should be more than 500. So this is not a correct statement. I don't think it is true. Now, in 1 year time, it will have 0 atoms. Really? I've done this here. 1 year to come. If now it has got 1,000 atoms, and in 1 year, half of it will be gone, then 1 year to come, it should not have 0 atoms. 1 year to come, half of what you have now, that 1,000 should go. So you have 500 atoms. So this statement too, I doubt if it's correct. It's not a true statement. So let's check. It says, which of the above are correct? Well, I've taken this and that. Let's see if there are possible answers. A, I and I only. That's interesting. B, I and I only. So I is correct, but I is not correct. So this will not fit for it. C, I and IV. Both of them are not correct, do not fit for it. And then D, I. Oh, it cannot be so. So the answer will be A, I and I only. And that's a past question for us. SSC 1995, 39. So it is just a test on your understanding of half-life. Okay, let's move on. I have an example 2 for us to look at. What does it say? Ooh, there's a diagram. 20 grams going to 10 grams going to 5 grams. Then it says 1 year, 2 years, and 3 years. Okay, what do we have to do? It says the diagram above illustrates a radioactive decay what is the mass of the substance originally? Originally. So 1 year ago, or after 1 year, we have 20 grams of the substance. After 2 years, it has decayed to half. Now you have 10 grams. After 3 years, it has decayed to half of what we had in after 2 years, 5 grams. So 20, half of it 10, half of it 5. So before, then there should be something here. You can guess it. This, half of it gave us this, half of this gave us this. So it means that whatever answer we get here, half of it should give us 20. It follows that logic. Let's look at our possible answers. 50. Half of 50 will give me 20? No. So this will be out. 10. Half of 10 will give me 20? No. This will be out. 20. Half of 20 will never give me 20. Out. 40. So if we put 40 here, then half of 40, 20. Half of 20, 10. Half of 10, 5. So 40 grams will be the correct answer. This is WASSCE Private Exams 2020. So I believe you have been able to understand all that I'm trying to talk about as far as half-life is concerned. Good. Let's move on. Now I want to take my time and go through the graphical representation of half-life so that we try to see if we can use this to get some other things for ourselves. So I'm going to draw a graph of, I'm going to get the vertical axis, and then I'm going to get horizontal axis, like that. I'm going to label my graph, and here I have the amount of the active nuclei initially present, and not. Then I have time. So let me draw my graph. Like that. So I'm going to look at first half-life, second half-life, third half-life. If possible, we go to fourth half-life. So I'm going to pick from here. So let me say T half and find out what will be left here. Then let me move to T2, or 2 times the first half-life. Right. So here. There we go. So 2 times half-life. What happens? What will be left? Then let's move to 3 times half-life. What do we have? Then probably I will end with 4 times half-life. 4 times half-life. Then we see what we're going to get. Okay, from our understanding, we are saying that after the first half-life, you should have half of the radioactive nuclei originally present, half of it should be left. So I'm going to get N0 over 2. N0 over 2. So when our time is 1, we have what is left to be N0 over 2. Okay. Now, the second one, when our time is now 2, half-life 2 times it. I'm going to get half of what is left. What was left is n naught over 2. So that will give me n naught over 4. So I'm going to get n naught over 4. Are you getting it? Now, third one. 3 times the half-life now is half of what was left, which is n naught on 4. So times n naught on 4, which give me n naught on 2 times 4, which is 8. So you're going to get n naught on 8. Last but not least, I'll just end with this one. Then if I have 4 times that, then I have half of what is also left here times n naught over 8. That'll give me n naught over 16. So I have n naught on 16. Are we seeing any expression, any trend? Yes. Here, I just have n naught over to the power 1. Okay. Here, n equals 1. So to the power, maybe like this, n naught on to the power n. And here, n is 1. Here, I can get n naught on 2 to the power 2, because 2 times 2 squared, give me 4. So here, I'm getting n equals 2. Then we'll get n naught on, this is 8, so 2 to the power 3. 2 times 2, 4 times 2, 8. So here I'm getting n equals 3. This, this is 1. Then here I'm going to get n naught on to the power 4. 2 times 2, 4 times 2, 8 times 2, 16. So here too, n is 4. Like that. So out of this, we can try and get an expression. We are getting, generally, you're going to get n naught, whatever is left, n, is giving us n naught over 2 to the power n. A very important relationship. So that's it. So in general, at any time t, the number of nuclei that remain unchanged or not decayed, the number of nuclei left yet to decay, n, is n naught over 2 to the power n. So when n equals 1, when small n equals 1, you're going to get n naught over 2. When small n equals 2, you get n naught over 4. When small n is 3, n naught over 8. If you should divide n by n naught, I'm going to get n over n naught is equal to 1 over 2 to the power n. This is a very important relationship. You have to take note of it. It will help you to solve a number of questions as far as this topic is concerned. Good. It follows that what then will be n? N is equal to the total time over half-life. Total time on half-life. So n equals t on half-life. Okay, so let's move on. We can try and make t half or the half-life the subject. You're going to get n from n. Here you have n equals t over t half. So t half will be equal to t over n. So the total time over n. Very important over the number of half-lives. Very important. Good. We can move on to what we call activity or decay rate. Don't forget we have looked at the n on the t, the rate of decay. So activity or decay rate. What will be our definition? It says activity is the amount of radioactive nuclei that decays per second. Activity is the amount of radioactive nuclei that decays per second. The amount of radioactive nuclei that decays per second is its activity. Or we can say activity is the number of decay per second. Activity is the number of decay per second. So number of decay per second, simple terms will be rate of decay. So activity in simple terms will be the rate of decay. So A is dN on dt, and I believe you understand why the negative sign is there. As the time progresses, the activity decreases because the amount that will be decaying per time will be decreasing. Half of the original will go, half of what is left will go, half of what is left will go, and all that. So A is equal to minus dN on dt. dN on dt is rate of decay. So we can say that activity is the rate of decay, the amount of radioactive nuclei that decays per second. So activity is simply the rate of decay. So in place of dN on dt, we could put A there, which is activity. Right. The unit of activity is becquerel, named after the scientist Henry Becquerel. So you could be asked in objective test, the one who propounded activity. So it's named after the scientist Henry Becquerel. He brought about activity, which is the rate of decay. So 1 becquerel equals 1 disintegration per second. 1 becquerel equals 1 disintegration per second. But usually, very often, the SI unit is per second. So when you're asked to calculate for activity, you leave your answer in the SI unit, which is per second. But sometimes, if the value of activity is given to you in a question, it may be given to you per week, per day, per month, per year. So there are other units that activity could be expressed in. But when you are supposed to find the activity, you calculate for it, then your answer, you leave it in per second. Per second. So activity or decay rate, you are saying that from dN on dt is equal to n. The very first thing we began with, the law of radioactive decay. Now from here, in place of dN on dt, we can put activity A there because the rate of decay is the same as activity. So when you put A in place of dN on dt, you're going to get A is directly proportional to n. So you're going to get A activity is directly proportional to n. In that case, when we take away the sign of proportionality, we introduce an equal to sign, and then we bring a constant, which is our decay constant. So A will give us equal to lambda n. A is equal to lambda n. All right. Note, if A naught is the initial activity of a radioactive element, the initial activity of a radioactive element is A naught. Just like we are saying that N naught is the initial amount of a radioactive substance present before decay. And A is the activity after a time t. They are trying to write our decay equation in terms of activity. So then A will be given as A is equal to A naught on 2 to the power n. Don't forget we had n equals n naught on 2 to the power n, like this. So it means that in place of n, you are putting a's there. In place of n naught, you have A naught, like that. like that. So A is equal to A naught on 2 to the power n. And we know what n is. Good. So we can write the decay equation in terms of activity as A is equal to A naught exponent minus lambda t, similar to n equals n naught E minus lambda t. So we are only replacing n with A and n naught with A naught, and any other thing is the same. Any other thing is the same. So depending on the question given to you, if it's in terms of activity, then you write a decay equation in terms of activity like this. If it is in terms of the amount of the active nuclei present, n, and what is left, then you go to n and then n naught. So A is activity after a time t, and then A naught is the initial activity. So we can get a graph just like we had a graph for n naught decreasing with time. We can also have that of activity. So A is activity, left after time t is the initial activity, and it says that the initial activity is decreasing with time. So the rate of decay is decreasing with time, because with time the amount that is left that's supposed to decay will also be decreasing. So the time at which it's going to decay, that it will be slowing down. With time, because the amount that is left will also be decreasing, becoming smaller and smaller with time. I think it's a good time to take a breather. We are going to solve some questions based on the things, the formula you have encountered. But I'd like to go on a break, get something little to sip, and then come back, and then we continue. So you can get up, stretch, move about a little bit. I will be back in a jiffy. All right.
Examination malpractice is any form of deliberate cheating on examinations which provides one or more candidates with an unfair advantage or disadvantage. It is an illegal act and can be perpetrated by a single individual or groups. It can occur outside or inside the classroom. So before you enter the exams hall, make sure you follow these instructions. 1. Empty your pockets and avoid entering with a foreign material, that is smuggling of answer scripts. 2. Avoid writing on sheets of papers, handkerchiefs, erasers, covers of calculators, and on the skin. Remember not to fall victim to any examination malpractices, so you could have a peaceful examination. Prepare well, and we wish you all the best. Joy learning, keep learning.
Did you know that examination malpractice can lead to poor grades? As a result of this, you will lose trust in yourself and will not be able to perform well in any future assignments and tests. So, I'm here to give you simple tips on how to avoid examination malpractice. So let's talk about the do's in examination hall. 1. Bring everything you need into the examination hall. It may sound simple, but a lot of stress can be avoided by making sure you have everything you need to do in the exam. Make a checklist the night before each exam, then go through it before you leave home, and then again before entering the examination hall. 2. Read the whole paper before writing anything. One of the most important exam preparation tips to dwell in during the run-up to exams. Read every question before you start writing anything. Don't get stuck in straight away. Read the paper from the start to finish at least once before you begin writing. 3. Do the easiest question first. There is no reason to do the question in order they are printed in the exam. Firstly, getting the first question done well will help you calm you and get you focused for the rest of the exam. Secondly, often you will get an easy question done quicker, so you will be ahead of schedule from the start. 4. Revise, revise, and revise again. The night before the exams is not the time to be trying to get your head around new concepts. Some students read and forget part of the information during exam. This is why you have to keep revising till the day or morning of the exams. This is one of the steady habits of highly successful students. Once you have become so conversant with your revisions, little or a slight pause will only be required for you to recollect the appropriate information. 5. Ask the invigilator questions. If you are stuck on the meaning of a word or can't understand what a question requires you to do, put your hand up and ask the invigilator who is supervising the exams. More often than not, they will help you or point to you in the right direction. 6. Look at the marking scheme. Keep an eye out for the marking scheme that shows how many marks are being awarded for each part of a question. If there are only small amounts of marks going for a part of a question, refrain from giving it the majority of your time. Instead, answer questions with higher marks. 7. Cross-check answers. You must check all answers before submitting your answer sheet to the invigilator. You should keep the last 15 minutes before the final bell to cross-check your answers. A thorough revision of every answer is necessary, as it will help you to identify the errors and make the necessary corrections. 8. Think about the consequences of malpractice. Ever heard the saying, "The fear of God is the beginning of wisdom"? Always remember, there is punishment for people who are caught cheating. There you have it. Believe in yourself, prepare well, and you will come out with flying colors. My name is Tina and I am your examination coach. Keep watching Joy Learning and follow us on all our social media platforms. Till I come your way again, shine on. Joy Learning. Keep learning.
It's time to wish your loved ones well on that special occasion. Is it the birthday or anniversary of your child, friend, classmate, your schoolmate, your teacher, or non-teaching staff of your school? The all-new JL Birthday Wish by Ghana's #1 educational TV channel hits your regular classroom screen. And as usual, it is time for Jack to play and have fun. It has been made easy for you, and this is how. Send a picture of your loved ones. Add their names, school, and location, and a heartwarming birthday message. And finally, follow us on official Joy Learning TV on Instagram, like the JL Birthday Wish post, and tag 5 friends. Send it to our WhatsApp line 0247 108 738. And voila! Your birthday wish will be aired on Joy Learning TV and all our social media platforms. Learning is made fun with the JL Birthday Wish. Joy Learning. Keep learning.
All right, welcome back. It's revision show time, and you can call me Pius. I've been here with you, taking you through something little on the law of radioactive decay, decay constant, half-life, and decay probability. activity and all that. It's a good time for us to try our hands on 2 questions. And then I want to remind you that in some few minutes time, I'm going to open a phone line so that you can call in. Okay, so example 1. An element whose half-life is 3 years has n number of atoms. How many atoms would have decayed in 9 years? This is WASI November 2019, question number 35. Now we're giving possible answers. A, 7 on 8 n atoms. B, 1 on 8 n atoms. C, 1 on 3 n atoms. And D, 2 on 3 n atoms. So we have to try and solve this question. We can solve the question by looking at, or by putting down the parameters. In the question, we have been given half-life, 3 years. So T half is 3. Now, the number of atoms present now is n. We were using n naught, so I'll say n naught equals n, but don't worry, with time, we'll replace it, okay? Then I asked how many atoms would have decayed in 9 years. So the time given to us T is 9 years. If you want to know the number of atoms that would have decayed, okay, in 9 years, well, then we have to look at what we have initially, what we have left. Then when we subtract, we'll know the amount that would have decayed. So in 9 years' time, what will be the amount of, or what will be the number of atoms left? Now that we have n number of atoms, in 9 years' time, how many will be left? When we get that and we subtract, we're going to get the amount or the number of atoms that would have decayed in 9 years. So let's set the ball rolling. So let's put our parameters. We have half-life, T half, to be 3 years. We have the number of atoms now. So I'll say n naught is n atoms. Then we have the time to be 9 years. Good. So number of atoms that would have decayed is equal to the number of atoms present initially minus the number of atoms left. After the decay. So let's move on. We have a formula telling us that n, what is left? You see, we know the number of atoms initially present to be n naught, and now I think it's n. So we know this one. Now I'm supposed to go and look for n, the number that will be left after the decay. Then you can subtract. So n equals n naught over 2 to the power n, right? So let's move on. What's our n? Our n is T on half-life, right? So we're going to get T, which is our 9 on our half-life, which is at 3. Now give us 3. So that's the case. I'm going to get n, it's giving me n naught on 2, 3. Which will give me n equals n naught over 8. But don't forget that our n naught is the n atoms, right? What is left? It will be the initial 1 over 8. But according to the question, n naught is the n. So instead of n naught over 8, we're going to get n over 8. So I'm going to get, from the formula, number of atoms present initially, which is n, minus what I have, n number of atoms left after decay. So I'm going to get n on 8. So this is 8 times 1. The coefficient of n here is 1. So 8 times 1, 8, minus 1 here. So just to make you understand, the coefficient of n here is 1. That of under n here too is 1. So 8 times 1 here is 8, minus 1 is 7, all over 8. So here our answer becomes 7 over 8n. 7 over 8n. Let's see if we have this in the possible answers. So 7 over 8n atoms is here, and that becomes our answer. So in 9 years' time, you're going to get 7 over 8n atoms that would have decayed. 7 over 8n atoms that would have decayed. Good. I think we can get another example. It says an isotope of radon has a half-life of 3.8 days. Calculate its decay constant. An isotope of radon has a half-life of 3.8 days. Calculate its decay constant. It's also a past question. WASI for school candidates 2016, question number 12. So as for question number 12, we had this question. So, like I mostly do, we start by putting down our parameters. For this question, we have half-life. So T half is 3.8 days. They are asked to find decay constant. Which is lambda. What's our formula? Our formula says half-life is equal to natural log of 2 on decay constant. So I'm going to get decay constant to be natural log of 2 on half-life. So decay constant give me natural log of 2 on 3.8, which will give me, with the calculator, you can easily get that, over 3.8, and that's going to give you an answer. 0.182. So 0.182 C per day. But when we looked at the units of decay constant, it was per second. So we could also have solved this question, leaving an answer or our answer in per second. I actually chose this question to make you understand that why can go as low as giving you very simple questions like this, just to test your understanding. So in that case, I would have to change my half-life, T half, which is 3.8 days to seconds. So I'm going to get my half-life to become 3.8 days times 24 hours in a day times 60 minutes in 1 hour times 60 seconds, making 1 minute. So 3.8 times 24 times 3,600 or times 6 times 60. That'll give me 328 320 seconds. So 3.8 days times 24 hours times 60 minutes times 60 seconds. So in seconds. So in that case, lambda will give me the log of 2 on 328,320 seconds. So I'm going to get that divided by that, and I'm getting 2.11 times 10 exponent minus 6 per second. So you can also change the half-life from the days to seconds, like I've done here. And then you follow suit with the procedure. All right. We can move on. That's another example. It says, a piece of radioactive material contains 10 to the power 10 atoms. 10 to the power 10 atoms. And has a half-life of 30 days. Calculate the number of the days required for 10 to the power 5 atoms to be left. So we have a radioactive material. It has got 10 to the power 10 atoms. So that becomes our N naught. So initially, you have 10 to the power 10 atoms. Then the half-life, so T half, 30 days. We are asked to calculate the number of days. So what we don't know is the time, number of days required for 10 to the power 5 atoms to be left. So this means that our N becomes 10 to the power 5. So let us try and put down our parameters and see what we can do about this. So I have N naught to be 10 to the power 10 atoms. I have half-life to be 30 days. We have N, number of atoms remaining, 10 to the power 5 atoms. And we are asked to find the time T. So we will go with our decay equation, which says N equals N naught E minus lambda T. But I can just pick it like this. I'll work this out separately. So T this way. So let's put things into perspective. We want to find T. We know N naught. With the information we have here, we can find T so that we can come back and put it in there. Let's find lambda. So I'm going to get T half equals that on that. So our aim ultimately is to find t, but we can find lambda out of the information given to us. Then we come and put it into the equation, manipulate it to find t. So lambda will just give us natural log of 2 on the half-life. And lambda will give us natural log of 2. What's a half-life? 30. So let's use our calculators. Get natural log of 2 all over 30, and that's going to give you 0.0231. Okay, so we can move on. So in place of n, I have 10 to the power 5. So I'm going to get 10 to the power 5 atoms equals, and n not 10 to the power 10. 10 to the power 10 exponent, are we good to go? Minus, then lambda is 0.0231, then t, which we don't know. So now the rest is our maths. We have to find ways and means to get what we want. Okay, if I divide both sides by 10 to the power 5, I'll get 1. So I'm dividing both sides by 10 to the power 5. Probably, let me just show it. So I'm going to get 10 to the power 5 on 10 to the power 5 equals 10 to the power 10 e minus 0.0231 t on 10 to the power 5. So ideally, I could just skip this step and move on. So this will give me 1, because they will cancel out. I'll get 1. Okay. Then from indices, 10 to the power 5 numerator, if this 10 to the power 5 should go up, we come to the power minus 5 to get 10 to the power 10 times 10 to the power minus 5, something like this. 10 to the power 10 times 10 to the power minus 5, which give me 10 to the power 10 minus 5, which is 10 to the power what? 5. So that should be okay with us. So I'm going to write 10 to the power 5 in place of all that. So I'm going to get 10 to the power 5, right? Exponent negative 0.0231 t. Let's keep working. What can I do? We can have 1 over 10 to the power 5. Okay, 1 equals all that. We are trying to take away this negative sign. So like I did, if I divide both sides by 10 to the power 5, I'll still get 1 over 10 to the power 5 is equal to e minus 0.0231 t. Let's move on. That will give me, I'll just repeat my last step so that you can follow through. So I have 1 on 10 to the power minus 5 equals e minus 0.0231 t. So 10 exponent 5, sorry, good. This could give me 1 on 10 exponent 5 is equal to 1 on e exponent 0.0231 t, so that the negative goes away. Then I can find the reciprocal on both sides to get 10 exponent 5, right, is equal to E 0.0231 T, right? All right. So we're going to get log of 10 exponent 5 to base E, right? Okay. Is equal to natural log of E 0.0231 T to base E. So I'm going to get that of 10 exponent 5 equals, now I'm going to get log of E to base E, so 0.0231 T times log E to base E. This will give me 1. That whole expression of log E to base E will give me 1 equal to 1. So I want to keep a natural log of that. So that of 10 to the 5 will give me 0.0231 T. So T will give me the natural log of 10 exponent 5 on 0.0231. So let's try to see if we get an answer. Divided by 0.0231. Wow, I'm going to get T is equal to 498.395 days. 498.395 days. So it's important to take your time and go through the steps. So right from the onset, from our parameters, we put down a decay equation there. Then we find lambda from this expression to get lambda to give us 0.0231. Then we move on, put it back into the equation. This is 10 to the power 5, 10 to the power 10, E minus lambda times T. Divide both sides by 10 to the power 5, so I could take this away. I got 1. Then this will be 10 to the power 5, E that. So, but again by 10 to the power 5, I want this to stand alone to get this. Then, to take away the minus, I bring this whole thing as a denominator. So I have 1 on that, so negative goes away, 1 on that. Then we can reciprocate to get this expression. We find natural log to base, or log to base E for both sides. And this log E to base E becomes 1. And this one I maintain it as natural log of 10 to the power 5, giving me this. Then I divide this by what's attached to T, its coefficient, and that gives us 498.395 days. It's a good time to open the phone lines so that you can try your hands on the problem of the day. You have seen the questions already. You can call in 0302211 The numbers will be shown on your screen. 0302211 or 0302211 706. 0302211 705 or 0302211 706. Kindly tune down the volume of your TV set when you call in so that we can communicate via your call handset, a mobile phone, or whatever you're using to call. Okay, and then try and give answers to the problem of the day. Very, very simple questions. So 030-2211-705 or 030-2211-706. So in the meantime, I'll try and do a recap on photoelectric effects. I'll be trying to take you through that. And when you ask me when your call comes in, I'll stop and then attend to you. So we can look at photoelectric effect. Other text will call it photoelectricity. So what is it? What is it? It is the emission or the removal of electrons from a cold metal surface. From a cold metal surface. When light photons or when electromagnetic radiations of suitable frequency is incident on the metal surface. So we are talking about having a metal surface. So this could be our metal surface. Then with this, there should be electrons on the metal surface. So when radiations are incident on the metal surface, these radiations contain tiny packets of energy, which we call photons. Photons. So when the photons are incident on the metal surface, an electron absorbs all of the energy of a photon. And then it's able to move out of the surface of the metal. And this phenomenon is called photoelectric emission, photoelectric effect. I guess there's a caller on the line. Hello, do you have anyone online?
Hello.
Hello, good evening.
Good evening, sir.
Your name, please, and where you're calling from?
My name is Saidi. I'm calling.
Can you speak up a little bit? I'm trying to hear you.
Hello.
Yeah, can you speak up a little bit?
Yeah.
Your name, please.
My name is Hayudi.
Okay.
I'm calling from there.
Okay, please go ahead. You want to answer the question?
Yeah, I want to answer the problem of the day.
Okay, please go ahead.
Okay.
Is it the first one?
From the equation, speed of light is equal to frequency times the wavelength.
Okay.
Making frequency the subject.
Did you say frequency times wavelength?
Frequency times wavelength.
Okay. Did you say C of light or E of light?
C.
C.
Yeah.
Okay.
Frequency of.
Okay, go ahead, please.
So making F the subject, the frequency will be equal to the speed of light over the wavelength.
Okay.
But the speed of light is given as 3.0 times 10 raised to the power 8.
Okay.
And the wavelength is given as 4.5 times 10 raised to the power negative 7.
All right.
Therefore, the final answer will be 6.67 times 10 raised to the power 14 Hz.
Okay.
And again, the energy of the incident light
Okay.
from the equation, energy of quantum radiation, which is equal to the Planck's constant times the frequency.
HF, okay.
But the Planck's constant is given as 6.6 times 10 raised to the power negative 34
Okay.
times the frequency, which is 6.67 times 10 raised to the power 14.
Okay.
Therefore, the energy of the incident light will be equal to 4.402 times 10 raised to the power negative 19 joules.
Good. Good.
And again, the energy of the photoelectrons emitted
What name will you give that energy? What name will you give that energy of the photoelectrons?
Energy of the incident light.
The energy of the photoelectrons. What will be the name? What's that energy?
Energy of quantum radiation.
Okay, that's the kinetic energy.
Kinetic energy.
All right, so please go ahead.
Okay, from the Einstein equation of photoelectric effect.
Good.
Making the work function subject there.
You want to rather make work function the subject?
Sorry, the kinetic energy the subject.
Good.
So kinetic energy will be equal to energy of quantum radiation, which is HF minus the work function.
Okay.
And therefore, doing the substitution,
okay.
The Planck's constant.
But you have already found HF, right?
Okay, so 4.02 times 10 raised to the power negative 19.
Okay.
Minus 3.0 times 10 raised to the power negative 19. So therefore, the final answer will be 1.02 times 10 raised to the power negative 19 joules.
All right. Very good. Very good. That's impressive. You have done justice to all the questions. You've solved for frequency of the incident radiation. You've solved for the energy of the incident photon. You've solved for energy of the photoelectrons. So my producer will talk to you, right?
Okay, sir.
All right. Thank you for calling. We appreciate your call.
Thank you, sir.
All right. So that was it. He called to answer question 1B, and he has been able to work it out completely, everything correctly. Bravo, well done, well done. That's impressive. That's impressive. You've really done so well. That's impressive. That's impressive. So he's done justice to that. He's giving us what the frequency of the incident radiation or the light is. Here's the energy of the incident photon. He's done all that he's supposed to do. That is very good of you. In fact, that's impressive. You've done well. Bravo, bravo, bravo. All right. All right. So, do I have a caller on the line? Hello?
Okay.
All right. Good evening. Your name, please?
Please, my name is Salama.
Okay. Where are you calling from, please?
Techiman.
Techiman. All right. So, we want to answer question number 1A?
Yes.
All right. Please, go ahead.
So, the evidence is 1.
Okay.
X-rays travel through a vacuum.
Good. X-rays travel through vacuum.
That's why they are claimed to be electromagnetic waves.
Good. Good.
And the second one is X-rays can be polarized.
Good. They can be polarized. Okay.
Yes. And the third reason is they travel at the speed of light.
Good. They travel at the speed of light. That's also good. Fine. So thank you so much for calling. My regards to everyone in Techiman watching us tonight.
Okay, sir.
Good. So today my students, my viewers have been able to really do justice to the problem of the day questions. So you see why I've been telling you that it's advisable to try your hands on question number 12. Why? Because question number 12 is manageable. Once you prepare for it, you will be able to just get all that you're supposed to get. All right. So thank you for calling. We appreciate your call. Thank you so much. All those watching us, thank you for calling. I have a caller on the line. Hello? 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 Hello, good evening. It looks like I've lost the caller. So we're looking at photoelectric effect. So we have electrons on the surface of the metal, and once the photons are incident on the surface of the metal, these electrons are able to gain energy, and then they move away. And this phenomenon is what we call photoelectric effect. Now, Einstein gives a very good explanation to photoelectric effect. Einstein is saying that when you have the photons incident on the metal surface, it happens that these photons carry a particular quantum of energy, and he represents that energy with E. Okay, so E here is the energy contained in the radiations, which is the photons. And then he tells us that part of this energy is used to do work. Part of the energy is used to do work. What is that work for? That work is to break the bonds between the electrons and the surface of the metal. So part of the energy is used to break bonds between the electrons and the metal surface, which you call the work function. Then Einstein says that part of the energy that is left becomes the maximum kinetic energy with which the electrons move away from the cold metal surface. Part of that energy left becomes maximum kinetic energy. I chanced on the marking scheme from WAEC, where students were supposed to write or state Einstein's equation for photoelectric effect. And then the marking scheme insisted that if students don't add maximum to kinetic energy, the mark should not be given. So when you are writing that equation, E is equal to W plus KE, which is kinetic energy, you have to bring subscript max, because that is the maximum kinetic energy. So we can define the work function, and we can also define the threshold frequency. We are saying that the photons that are going to incident on the metal surface, they should come with a particular kind of frequency, a suitable frequency called the threshold frequency, and F naught is used to represent threshold frequency, F naught. Now, what we are saying is that when the photons are incident on the metal surface, if they don't come with the right or with a suitable frequency, they will not cause photoelectric effects. They will not cause photoelectric effects. They must come with a suitable frequency, which you call a threshold frequency. And when that happens, we are going to have electrons gaining all the energy of the incident photon. And in that case, they are going to come out of the metal surface. So I'm going to get E being the energy is equal to the work function plus maximum kinetic energy with which the electrons will move out of the metal surface. Now, if you make Ke max the subject, Ke max becomes E minus W. Now, E is equal to Planck's constant times frequency, and W is equal to HF naught, where F naught is called threshold frequency. Threshold frequency. So we can get this equation to be Ke max is equal to HF minus HF naught. And this equation is called Einstein's equation for photoelectric effect. Einstein's equation for photoelectric effect. This equation can help us solve a number of questions. From this equation too, you can try and draw a graph. Now, I want to compare this equation with the equation of a straight line. Y is equal to mx plus c. So if I'm comparing, then Ke max should be on the y-axis. Then I'm going to get frequency on the x-axis. Then the gradient, I'll come to it, Planck's constant. Then I'm going to have an intercept, c, and this whole expression, hf naught, becomes an intercept. So should we try to get a graph? Like this. So I want a graph like this, and I'm going to plot Ke max here on the vertical axis against frequency F. So if this will be in joules, this will be in hertz. Now I'm going to get a gradient M, which is positive H. Then I should get an intercept on the negative axis. So my graph is going to rise, but it will not pass through the middle, or let me say the origin. It won't pass through the origin. It's going to get an intercept on the negative axis this way. So this place will be my intercept on the negative axis. So this is the same as minus HF naught or minus W. And here I'm going to get F naught, which is the threshold frequency. Then if you should find the slope of this graph, Y can draw this graph for you, label portions, and ask you to identify those portions. So this becomes my slope, and my slope represents the Planck's constant, H. My slope represents the Planck's constant, H. All right. Right from this expression too, you can see that Ke max is directly proportional to HF, which is E, the radiations, the energy of the radiations. Now we have what we call fundamental characteristics or properties of photoelectric effect, which are similar to something like laws of photoelectric effect. One of them is that the kinetic energy of the photoelectrons. What are photoelectrons? Photoelectrons are simply the electrons that are emitted out of the cold metal surface when photons of suitable frequency are incident on the metal surface. So if you have photons with the right frequency hitting the metal surface, the electrons that go out, that are emitted as a result, they are called the photoelectrons. Now, the energy of these photoelectrons, kinetic energy, which they move, that is proportional to frequency of the incident radiation. Very important. It is not dependent on the intensity of the light that is incident on the metal surface. Rather, it is dependent on the frequency of the incident photon. Now, for every metal too, there is a particular frequency of the incident photon below which there will not be emission of the photoelectrons. So I'm trying to say that every metal will have a particular frequency at which the photons should incident on it to cause the electrons to be emitted. To cause the electrons to be emitted. So, as you prepare for the exams, you should be able to get this in mind. We have a caller on the line. Hello, good evening. Your name and where are you calling from, please?
Hello, please. My name is Peter.
Okay, please. Where are you calling from, please? Where are you coming from, please? Okay, at this juncture, we won't be able to pick any more calls. We won't be able to pick any more calls. But as I was saying, as you are preparing for the exams, you need to understand some of these things. Why I could not really ask you to state the laws of photo effect? No, but rather you'll be given scenarios, like maybe in a photocell, what will affect or what will influence the rate at which photoelectrons are emitted? Or in a photocell, what will influence the energy with which the electrons will move? Okay, so you need to consider all these things. Now, we had a question about X-rays, and we're asked to tell or give evidence that supports that X-rays are electromagnetic waves. So, what are electromagnetic waves? Waves that can travel through both vacuum, so they can go through vacuum, and they can also go through a material medium. So waves that can go through both vacuum and a material medium. So if there is a vacuum, they go through. If there is a material medium, they go through. We call them electromagnetic waves. Then these waves have got some properties. And like the caller said, they travel in straight lines. They travel in straight lines. That's one. Two, what else can they do? They travel with a speed of light in vacuum. To travel with speed of light in vacuum. They move with the speed of light in vacuum, which is 3.0 times 10 to the power 8 meters per second. Now they can be polarized, or they can be polarized. So these are the answers that the caller gave. Now I want to focus on what we call X-rays. Then we can draw the curtains for tonight's revision show. What are X-rays? Some time ago, X-rays were used in the medical field for something which is no more so, because now we have what we call the ultrasound scan. But still, we can use X-rays to detect bone fractures. You can use X-rays. Normally, you go for X-rays to check what is going on with the bone, what is going on. If there's a fracture, you want to locate where it is. X-rays can do that for. X-rays can even help us locate maybe a swallowed object. So, what are X-rays? production of X-rays is an application of what we call thermionic emission. So, thermionic. So, I want to take the opportunity to talk about this because we're talking about photoelectric effects. Now, in photoelectric effects, you have photons incident on the metal surface. Electrons gain energy, then they move away. In thermionic emission, you have a metal, and the metal is heated to a sufficiently high temperature. As a result, electrons are emitted from the hot metal surface. So the emission of electrons from a hot metal surface, when the metal is heated to a sufficiently high temperature, is called thermionic emission. And those electrons that are emitted are called thermal electrons. So they are electrons emitted from a hot metal surface when the metal is heated to a sufficiently high temperature. Now, to get X-rays, you must get what we call cathode rays. Cathode rays. So, let me just get this as a cathode. Then I have a heater attached to my cathode. So this is my cathode. A metal, negatively charged. Then I have an anode. So let me see this one. This is my anode, positively charged. This is my anode as a target metal. Now, when the cathode is heated, when the heater heats the cathode, the metal gets heated to a sufficiently high temperature. Electrons then go away from the cathode. So, stream of electrons, which we call the cathode rays. So, stream of electrons called cathode rays. They move from the cathode. And because they have a negative charge and you have a positive anode in front of them, they accelerate towards the anode. So they come to hit the target metal. But they cannot penetrate through the target metal. They cannot go through the target metal. So what happens? They hit it, and as they are moving, they have kinetic energy. So as they come to a sudden stop, they are going to lose some energy. In losing energy, they give off radiations. Radiations. These radiations that are giving off are what we call X-rays. That's what we call X-rays. So X-rays are electromagnetic radiations. Simple as that. X-rays are electromagnetic radiations that are emitted from a metal surface. When that metal is struck by fast-moving electrons, they are what we call X-rays. X-rays. So X-rays are electromagnetic radiations that are emitted from the metal when the metal is struck by the fast-moving electrons. The electrons will give off radiations, and then we have what we call X-rays. So usually we will just say the X-rays are electromagnetic radiations obtained or produced when fast-moving electrons are stopped by a target metal. I think that's all time we're going to permit us to have tonight. Tonight we're able to look at the law of radioactive decay, look at the decay constant, look at the decay equation. So, as we prepare for the exams, read around these lines. Do not forget the equations that you will need to recollect as you move on. And then try your hands on some of the past questions and the decay equation, decay constant, half-life. And then you should be able to tell that you are really poised for the exams. And then we will get you covered here on the Joy Learning television channel with what you should expect and what you should keep handy. Okay? So as we go through the week, make time with us here via YouTube or via Facebook. Then we would be able to help you get up to date with what you're supposed to know. In our next show, we'll try and look at other areas too that you can master as far as the exams is concerned. So you stay glued to Joy Learning Television, and we say you keep learning. All right, so with the lesson coming to an end, you need to know some properties too of X-rays. X-rays have a very high frequency. That is to say, the rate at which they can move through matter and out of matter per second is very fast. So X-rays have very high frequency, but they have a short wavelength. Okay, so when you draw the electromagnetic spectrum, you are going to have X-rays as part of the spectrum, right? Maybe in increasing order of frequency. If you do that, you see X-rays come just before gamma rays. X-rays come just before gamma rays, telling you that X-rays have a very high frequency. But if you have C equals F lambda, F equals C on lambda. So frequency and wavelength are inversely proportional. In that case, if they have a very high frequency, then they are going to have a very short wavelength. All right. So we want to thank you for having us with you tonight for the show. It's been nice having you. I'm grateful to the callers who called in and answered the question of the day. So, till I come away another time with an exciting physics lesson, and then probably Albert is my name. Call me Pius. Keep watching Joy Learning television channel and keep learning. Have a good night. It's bye-bye for now.